Okay, so the assignment states is that we need to prepare a design for the monitoring available system parking garage that can hold up to BFH cars, which can be counted from the ID. And in this figure, the count we need to actually show if it's actually full in the capacity, or if the space is available in the second segment display. Blinking to another display with a 77 display. There are actually sensors for entry and exit that could be used to count the numbers of the cars getting out and in. So for this approach, we actually need to first build the we actually need to first with the block diagram. And first, for the ID, I have my ID around here, which is 235448893, and I can also show the number of A, B, C, D, F, G. And for the maximum car output, we need to add D plus F plus H, which is 3 plus 8 plus 3, 14 number of cars. So the block diagram is like this. First, there are two types of sensors, where is entry sensors and exit sensors. We actually assign the variable for the for that u, that means u equals to 1 when the car is entering, and u is equal to 0 where the car is exiting. And then for that, sensors goes to the up down counter, where it gets incremented or discriminated depending on by 1 depending on the car, if the car is exiting or entering. Then also, after updating one time, we compare the count number with the number 9. If it's equals to 9, we actually display full display, and if it's not equals to 9, that means if it's not equals to 9, we actually display the space available. So this is the flow diagram where we start, and the starting state, the counter is 0, and when we go to the sensor, it gets activated. Sensor activated. For if it's gets activated for the entry sensor, we actually counter, that means the count number plus 1, that means 1 car entered. And if we gets exited, that means count minus 1, that means we decrement the counter number by 1, and then it's submerged to the counter. And then we actually compare the counter with 9, and if it's true, that means the counter is equals to 9, that means we display fulls. And if it's not true, if the counter is not equals to 9, we actually display space available, and this then. And this process also gets repeated every time the sensor gets triggered. This is the counter architecture. The entry sensors counter is plus 1, which is up, which I actually previously stated that u equals to 1 for the counter up or the entry, and u equals to 0 for the down counter. And this is how the states goes from 0 to 14. We actually showing the number of outputs for this 0 2 1 2 3 4 5 6 7 8 19, and that means 14, and this is the number of 14. We also use the 4-bit synchronous BCD decade counter mode 15, which actually means we can actually show 0 to 14 counts for this the number of cars for there. And this is the state table. So this is 0 1 2 3 4, and we actually showed for every step the next step. If u equals to 1, that means 1 car enters, and if there is 0 cars, if 1 car enters, that means it gets 1 incremented by 1, that means 1 value of the counter. And if the next state is gets let's say there is 2, and if the next state is gets minus 1, that means decremented by 1, or 1 car exits, it gets decremented by 1 value, that means 2 to 1 we actually shown here. And this is for the all possible state, all possible number here is there. And for the clock here used in this counter, we actually use the exit or entry sensor. That means when the sensor, the whole sensor exit or entry gets triggered, it actually will act as a pulse for the clock. That means when any of the entry or exit gate sensors gets triggered, it will pulse the clock, and it will trigger the whole counter. And this is how that we actually this is how that we actually designed the counter. For that instance, when we see this is where this is after the BCD mode 6. Before the mode 6, the EZ feature something like that. That means, for example, when it's 1 0, that means 2, and we need to move it to 3, that means 1 1. Where the for this, let's say Q naught, and this is Q1. Okay. As the Q naught gets updated in every pulse, we can actually say for K1 and J1, J0 and K0 equals to 1. That means for every pulse of the clock, the Q naught gets updated. That means if it's 0, it gets 1, and if it's 1, it in the next state it gets converted to 0. Let's say for Q naught, we need for this Q naught, we actually implemented the logic like this: U Q naught plus U Q naught U Q naught, and then we actually do this like this: U naught Q naught. This is like this. And how this works, that means this is for the entry and this is for the exit. Okay, so how does this work? Let's say for this condition, we need equals to U need equals to be 1 and Q naught equals to be 1. U equals to 1 means the car is entering. That means when it needs to have the car enter plus Q naught, the previous the Q naught in this present state, it needs equal to be 1. Let's see the state here where this is Q naught equals to 0, and this state which is here, Q naught equals to 1. Let's say let's actually just do a different example where this is 0 1 and 1 0. For this it is 1 to 2, right? This is how it moves. So when the 1 this is there is Q naught equals to 1, and if it gets incremented, that means U equals to 1, that means the enter sensor gets triggered. So which means it actually does this Q1, where it's actually not Q1, it actually means J1 K1 equals to 0. That means J1 equals to K1 equals to 1. It becomes 1 because the condition here gets true. So when this gets true, the number Q1 pulse get updated. That means if it was 0, it gets to 1, and if it was 1, it gets to 0. Like this is how the pulse of this is completed. So let's see how this goes there. And for the Q naught, it actually gets updated for the every pulse of every clock, and if that it is not Q1, for Q1, let's say for this specific state, the Q1 gets updated. That means 0 becomes 1, and this is how the state for the entry goes up. For let's say there is another step where I didn't show it previously, where it's 1 0 1 1. That means for this Q naught equals to 0 but U equals to 1. That means this condition doesn't apply for this condition. J1 E1 equals to, if it needs to be 1, it doesn't apply to any of this condition. That means J1 and K1 becomes 0. So if it's 0, that means the previous step or the next step of the Q1 doesn't get updated for this value. That means if it's 0, it stays 0, and if it's 1, it stays 1. Let's see here. That means this is Q1. It was 0 from the first state, and it also 1 for the it was 1 for the first state and also 1 for the second step. And this is how the logic works for entering. And for exiting, we already saw that Q naught and U naught Q naught equals Q naught and Q was N, like that means exit or U equals to 0. This is for the first, and second one is Q naught equals to 0. Let's say for the previous example we already saw it here. Let's say from 0 1 to 1 0, like this. That means I had two cars in my garage or in my parking slot, and one car exits through the parking cars, number of cars becomes 1. Then how does it works here? Let's say q naught equals to 0 and u equals to 0. That means the L1 equals to, the K1 and J1 equals to U0 Q0 condition gets triggered. That means this equals to 1, and if it's 1, that means the Q1 pulse changes, which means if it was 1, it gets updated to 0. This is how it works. And let's say it was 1 0 and 1 1, so that means there was 3 cars and the one car moved, that means it becomes 2 cars. And how does this work? Same example. That means there is q naught equals to 1 and u equals to 0, which means u naught q naught. This is the condition. It doesn't apply, it doesn't gets applied in the condition for any of the condition we already assigned for J1 K1 here. That means nothing, J1 equals to K1 equals to 0. That means the condition here doesn't get fulfilled. That means the number is 0. That means, which means Q1 equals Q1's value stays the same. Which we can already see here, that there is the 1 is already there. And this is how for the Q1 we actually build the logic Q0 plus U Q0. This is how we build the logic for Q1 Q0 and U0 Q0. And for same logic we can build for Q2, which actually involves just multiplying the Q0 here, just and get Q0 here, and also just like this. For Q3 we can actually do the same. And this is how this the initial input goes. And for as we can see the number here for the last number, let's say here, right, for 15 the number is 1111, and for 14 the number is 1101. This is for 14 and this is for 15. But this is invalid because we don't want to go here. We actually need the mod 14 number. When the 14 comes, it will go up to 0. That means it needs to get reset. So what does we do? We actually need to exchange this value to 0000, which actually means 0. So how does it do that? Let's see. This is the number. It actually is 1 to 1. That means Q0 stays 1 to 1. That means it's forcefully toggle. That we need to actually toggle this value to get the 0. And this for here is 0. That means we need to actually forcefully stable the value. That means we cannot toggle, we cannot let this digit gets toggled. For this too, we actually also need to make sure that it doesn't stay stable. It needs to toggle for becoming 0000. And that's how we actually build the logic with this circuit J0 K0 equals to forcefully staying forcefully stable, and for this tree we actually need to forcefully destable. And this is how the okay, for the second part of the video, this is where we actually need to get two types of timer, where we have two timers, and we need to show a display on sequence of the display. That means if the parking lot is full or if is there space available, right? And for that we actually are going to use two timer, 555 here. 555 monostable timer. It will be continuously displaying for the full, and for the blinking display 555 astable timer, which actually will do the oscillation and the blinking part. Here is the simple diagram for the monostable, and we actually need to do the calculation for this. So here is my ID. So we actually got the A B C D E F G H ID flash. For that means we need to calculate the P, and for the P calculation we already got, we need to add up to A, B, E and G and multiply that by 2, which actually means we get 22 for the digit. We get 22 and multiply by 2, which actually gets us to 44. And the frequency calculation, we actually need to add AC plus 5. That means is 2 plus 5 plus 5 is 12 hertz. How the duty cycle works, that we need to subtract the p value from 100, which actually means the percentage of the duty cycle we actually get there, and the time period is 1 by f. That means the frequency, we actually need to inverse the frequency where we get the time period. For high time, we got the percentage here, 56%. We actually converted to 0.56, and then we multiply it by the time period we got from here, and we got 46.66 ms microsecond. And for low time period, we just do this equation like this, where we get the 38.33. then means the on time is 46.66 meter per second, microsecond, and the off time is 38.33 microsecond. This is the equation that we already have. So as the time high is greater than time low, we actually get the relevant resistance from calculating through these equations. Where the capacitor value, we actually selected three capacitor value, 50 to 250, 250 and then 470. This is the three types of capacitor, and then we calculated the RO2 and R1 through it, which we got the value. And for the 250 capacitor, we actually got some good values for R, which is 220 and 48, which can roughly equivalent to 50 ohm. So that means this is actually the more available resistance for and also cheaper. So we actually gone for this 250 capacitor for this type of application. So now let's go for the third question, where we actually designed two finite machines for counting the finite system machine with counting the state for A and B. Let's say the time period that we have here is t equals to 1 millisecond, and from the previous we got th and tl equal to 46.66 and 36.33 meter. That means the both of them are is greater than 4, which means we can actually convert them both of them to 4 ms meter, and A equals to 4 and B equals to 4. For this actual segmentation, we got the two states here. The two state in this there are two state. For the first state is not, we actually got A value. For the A value, it is high. For S not state, and B is equals to low. Same when S1 state is there, we get A equals to low and B equals to high. This is how the finite system machine works. Finite state machine works. Each state duration is controlled by the clock pulse, and every pulse is 1 milliseconds. Every pulse is 1 millisecond. So we can see the S0 state is goes for 4 millisecond. S0 state goes for S1 state goes for tth millisecond. That means S0 actually goes for th, and S1 actually goes for TL, which actually means 4 milliseconds, and it doesn't exceeds this time limit for this equation. And this is how we actually this is the state diagram, and this is the state table for all of this. This is the output A and B, this is inputs, and this is reset for everything like that. And this is the HADL code, where we actually followed the output system for this HCL code. We the output, since this is a mono first type FSM, the output depends only on the current state. That means this HDL is designed with that keep in mind. And for the question here is identify any drawbacks and limitation for part 1. That means we need to identify the limitation for this. Can only handle this machine can only handle the limited amount of cards due to the set. We already got the amount of card is for 14. The use of segment display for limit text, that we are showing two types of text, fulls and space available. So we cannot actually show more than those two words because this is the limited space. For that, the 5.5 timer doesn't built in enable pin, which reduce flexibility control. And also enter exit cannot be recorded at the same time, because the two the sensor is using only one counter. So that means if the card is entering and exit, another card is exiting at the same time, it cannot be it cannot register properly. Performance: this system performs reliably on a small parking slot. This the synchronous counter ensures reliable counter, and however performance may degrade for due to the system longer input. That means more input equals to more unreliable counting. Possible improvement can be done by using a microcontroller or FPGA can be used to reduce hardware complexity. That means the complexity that we already have, it can be also reduced through a microcontroller. LCD display can be exchanged with the 7-segment display, which can ensure the display of longer text. And additional sensors for improvement. That means we can also use, without the two sensors, we can also use additional sensors for more accurate indicating for the pulse, which actually indicates the whole assignment. Thank you.